So the Human Computation Institute is a nonprofit AI research institute, and we specialize in a sub-area of artificial intelligence called human computation. And human computation is an area that seeks to combine the complementary abilities of humans and machines to solve problems that neither can solve alone. So the human brain is possibly the most complex information processor in the known universe, and it's a highly intuitive neural network. It's so powerful that it can actually accomplish some symbolic processing. And if you've ever worked with neural networks, it's not an easy thing to do. And this is what gives us the ability for language. But it's not the most powerful symbolic processor. Machines are actually designed to do symbolic processing, so machines are good at calculating, arithmetic, very good at remembering things, executing a process, doing logical inference, and that sort of thing. So you can sort of imagine an AI timeline where, as machines become increasingly sophisticated, they're gradually kind of annexing these uniquely human capabilities. But so far, there are still some human capabilities where we seem to have an edge, such as abstraction, world knowledge, and creativity. One application of human computation is to use it to solve problems through the modality of citizen science. So citizen science is basically just, as Dr. Kim said, public participation in the scientific process. So it's where we engage public volunteers in some either data collection or data analysis. And this has been applied to biomedical research, among other areas. For example, with the Philo project, which engages public volunteers in genomic sequence alignment, the Foldit project for optimizing protein folding, the iWire project, which is involved in mapping the retinal connectome, and then Malaria Spot, which is a project that looks for malaria parasites in blood smears. So at the Human Computation Institute, we became acquainted with some Alzheimer's researchers at Cornell University, and were interested in applying the methods of citizen science and human computation to accelerating Alzheimer's disease research. The folks that we're working with there are interested in understanding why there's this 30% reduction in brain blood flow that's typically seen in Alzheimer's patients, and in particular looking at this through the lens of capillary blood flow and capillary stalling. So they made an important serendipitous discovery, which is that when they had, so they're studying this using mouse models of Alzheimer's disease, and when they had transgenic Alzheimer's mice with stalled capillaries, when they were able to restore blood flow to the capillaries, they saw a complete restoration of blood flow, and the cognitive symptoms of these mice abated. So this was very exciting, and it created the need to find a safe treatment that could restore blood flow. So the one that they tried was not a sustainable treatment. And this required conducting lots of imaging on mice that had been given different kinds of chemical compounds and drugs. And for each imaging session, which would last about a week, it would take 6 months to a year to analyze the data. So the question was, could we engage members of the general public in this analysis to speed up the quantification of this capillary stalling phenomenon? So we created an online game called Stall Catchers, which actually sort of gamifies this analysis, and we were delighted to discover that some people actually like doing this activity. In fact, today we have over 50,000 registered Stall Catchers players. On any given day, 50 to 100 different people are playing stall catchers, and consequently we're accomplishing the research much faster, answering research questions every 1 to 2 months instead of every 6 to 12 months. Some of the research questions that have been answered through the stall catchers analysis have resulted in top-tier journal publications, and we actually credit the public volunteers and their contributions when the journals will let us do that, and we'll hyperlink to a list of the usernames of all the contributors in the order in which they contributed. Part of what makes it possible for us to achieve very high quality research data from an analysis that's conducted by an untrained member of the general public is we use this wisdom of crowds technique. This relies on the fact that everyone sees the world and thinks about things a little differently. So it's this diversity of cognitive styles and how we see things that makes it possible for us to combine many different answers about the same analysis in order to come up with one expert-like answer. So when we began the Stall Catchers project, we were really just interested to see, is it possible at all? Is there some number of answers we can combine, if we do it in a sensible way, that would lead to an expert-like analysis? And what we found in our initial validation study is that somewhere between 15 and 20 people answering about the same capillary would result in a very high level of sensitivity and specificity, which met the data quality targets of our research collaborators. But 15 to 20 people is a lot, and it didn't seem very efficient, and we felt we could do better. We also realized that some people were just intrinsically better at the task than others. Some people learned to do the task faster than others. And we also realized that we were getting engagement from people in the Alzheimer's community, caregivers, and in some cases, early stage Alzheimer's patients. And in Alzheimer's disease, as some of you may know, there's the sundowning effect where there's this kind of cognitive slump in the afternoon. So we wanted to make sure that anybody could participate meaningfully in this analysis. And there was this kind of multiple constraint satisfaction problem that we had to solve. How do we make the analysis more efficient, and how do we include everyone in the process of analyzing the data? And what we discovered is that we could actually monitor player performance in near real time, so that we could adjust the weight of each person's answer based on how they were performing in that moment in time. And in doing so, not only were we able to include people who are experiencing some intermittent cognitive difficulties, but also that we could reduce the number of answers that needed to be combined from 20 to about 7. And actually today, on average, we combine about 4.5 answers to achieve an expert-like answer. So after running stall catchers for about 4.5 years, we'd collected about 12 million human-based annotations, and we realized there was an opportunity to train a machine learner to try to do the same analysis. And in this machine learning competition, there were about 900 participants on 70 teams, resulting in 70 new machine learning models. And an interesting thing came out of that. When we looked at the bias of these machine learning models, it mapped quite closely onto the distribution of bias observed in the human participants. And so we realized there was a potential opportunity to exploit that bias and that diversity. But we thought that bias by itself might not be so meaningful if it doesn't represent true differences in how the information is processed. So we looked more closely at the top 3 machine learning models and saw that indeed they were fundamentally different in how they approached the problem of classifying stalled and flowing blood vessels. So we decided to leverage this bias by giving agency to some of these machine learning models so that they could participate along with humans in the stall catchers game. We created an API, and we enlisted the help of the of the top 3 model developers. And then we ran a study where we incorporated these machine learning models as players, bot-powered players in the stall catchers game. So instead of having a wisdom of crowds approach, we called it a wisdom of agents approach, where we have both human and machine-based agents all contributing together. And so when we looked at a replication of a previous study where we had human-only cohorts using our standard wisdom of crowd methods, we saw that with a bot-only cohort, when we combined answers from multiple bots, it did slightly worse than the humans. But when we mixed humans and machines together, it was kind of like there was this additional level of diversity that had this kind of felicitous outcome of producing an even better result. And we have this kind of ethical standard, which is at the Human Computation Institute, where it's sort of our version of the Hippocratic Oath. We say, first, use no humans. If there's a way to solve a problem using machines, we shouldn't ask a human to do it. So there's this opportunity now to reduce the number of humans needed to do this stall catchers analysis, and which is consistent with our ethics. So we're leveraging the AI bias actually as a way to reduce the burden on humans. And ultimately, our goal is obsolescence. We want this to be a completely machine-driven process. So then what happens to the humans who are playing stall catchers? Well, we're always developing new citizen science projects. So there's a pathway so that the humans can move on to a project like this one, which we call beta catchers, which is about analyzing whole slide images of brain tissue obtained from Alzheimer's decedents in order to analyze the different kinds of plaques and other pathologies. So that's the application of AI to the ethical engagement of human communities in analyzing data. Communities that not only include volunteers who are analyzing data, but where some of those people are actually patients as well. But there's still this question of, what about our ethical blind spots? Those are the areas where we know we can do something positive with respect to ethics. And sometimes we're actually caught off guard. So this happened. We run an annual international event with stall catchers where we engage countries all over the world. In fact, our organization is globally distributed, which is wonderful because you get this sense of everybody around the world kind of coming together to tackle this problem that doesn't discriminate. But something interesting happened, which is when we reached out to the Citizen Science Organization in Central America, they had some questions to have answered before they would agree to participate. And they said, what's in this for us? If we make this effort and we participate in the Citizen Science Project and you develop a treatment for Alzheimer's, will we even have access to this? Because we've seen this before. And I had to go back to the biomedical collaborators and say, well, will they have access? And so, the answer had to do with off-label use of existing drugs, but it wasn't a very satisfying answer. And this was a blind spot that we weren't aware of. And we realized that, increasing the transparency of the potential impacts and benefits was important. Another blind spot that came up was we were engaging with Microsoft Research on a human-AI partnership experiment. So we were interested in testing the hypothesis that if you had a little bot that was only as accurate as its human counterpart, but had a different kind of bias, if they could work together to answer questions more effectively about whether a capillary is flowing or stalled. And we realized that running this experiment meant that we were sort of not just testing a platform and a citizen science project and a human computation approach, but we were also doing a behavioral study in a sense. So we thought it would be prudent to put it through an IRB process. And what we realized is that as we went through that process, there were a lot of questions that just didn't make sense for what we were doing. So these experiences inspired us to seek to reinvent ethical review so that it could address different kinds of emerging technologies like AI and human computation. And in this new framing of ethical review, the idea is that we actually employ an AI system to facilitate the review, that we have ethics that are codified, and that there's a sort of a decision tree. So the project stakeholder has a very efficient process of only answering the questions that make sense to the stakeholder. And we also appeal to legal, the kind of approach that the legal system uses of precedents, where we store a repository of prior projects and ethical outcomes, and use that as a basis for a more efficient analysis of the project. And we engage a community, which includes not only AI experts and biomedical experts, but also impacted communities, patients, and other people who might be impacted by the technologies that are being evaluated, so that they can have a voice in that and raise issues that others in the community might not be aware of. And finally, we store this set of ethical guidelines and allow for amendments to occur, so that if there's an emergent technology for which ethical guidelines do not yet exist, there's a mechanism for introducing new ethical guidelines and ensuring that those do not conflict with the existing list of ethics. And we've built an engine to already do that deconfliction, but the part we're still working on now is coming up with a way to crowdsource a set of values, which of course is a challenging problem. We've examined the use of AI to implement ethics and to help govern the evolution of the ethics themselves. We've learned that AI can be used as a tool for implementing engagement ethics, both to empower Alzheimer's patients to accelerate their own treatment research, and to reduce the burden of analysis by measuring and exploiting AI bias. We've also learned that AI can be used to ethically orchestrate the ethical review of new AI applications, both by including the voices of impacted populations and by providing a mechanism for adaptive ethical standards that can address unforeseen or emerging AI capabilities. And ultimately, we can sort of envision a virtuous cycle in which AI enables community-driven ethical standards to co-evolve with emerging technologies, which themselves will mediate future community engagement. Thank you very much.